Okay, so this is another video which is sort of outside of the official material for the Math 1410 Linear Algebra course, just giving you an overview of the basic ideas for writing proofs. Now, as we've mentioned in class, most of the times you're not going to be asked to write proofs in this course, but you will occasionally run into scenarios mostly on assignments where you may be asked to give an argument showing that something is true. And usually on the term tests, I try not to put too much theoretical content. The final exam, you might see one or two problems where you've got to write down some sort of proof just to find out, who was really doing their assignments all year long and who was just getting their friends to add their name to the group assignment page. Um, there are a few different types of proofs that we consider in this course, and they sort of depend on the type of statement that you're trying to prove. But before we get into that, let's just kind of give a quick overview of why bother with proof. It's not something that you usually see in your grade school mathematics courses, and then suddenly you hit to university and everyone's talking about proving things, and you often hear comments from people about how they 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 were okay with math, and then suddenly they started doing proofs, and they wish they could just get back to the math part and stop doing the proof part. But the bad news is that in fact mathematics is proof, and anyone that's actually engaged in actively doing mathematics is more or less engaged in proving theorems. Of course, they've got to come up with the theorems in the first place. But so the thing that I suppose sets math apart from other disciplines is that um, you know mathematical results don't necessarily have to have any connection with reality. Often they do. A lot of mathematics is very applicable to the real world and to other sciences, and that's why people are interested in it. Well, that's why some people are interested in it. Some people just sort of like it for its own sake, for solving the puzzles that come up. But um, so there's no way to kind of go out and test things experimentally, if you like. I mean, that's not entirely true. There are some people that do sort of experimental um, mathematics, if you like. But you know, the way that you determine something is true in math as compared to other sciences is by actually providing a rigorous logical argument that anyone who sits down and discusses that argument, goes over that argument, reads that argument, that there's common agreement among anyone who reads that argument that yes, in fact, all the logical steps you've presented here are correct, and I can agree that the conclusion you've come to is valid. And and one of the reasons that you kind of go to this trouble is that you don't really want to go around doing mathematics on a case-by-case basis. You don't want to have to kind of come up with a new result every time you change the numbers. You want to come up with general results so that, whatever sort of, situation you're in, whatever numbers you want to plug in, whatever, however you're thinking about this, that you can proceed with your calculations or whatever it is that you want to do, no, confident that as long as you don't make any errors, you're going to come out to the right answer because somebody has established this firm logical foundation that you can be confident in, so that everything will work out. So this is kind of where mathematics is powerful, is in this universality, that and any statement you write down, you can be confident that that statement will be valid in whatever context it happens to apply. So proof is the means of establishing this validity. And how does this work? There are a number of different types of statements that you might make in mathematics. A very common one is a so-called conditional statement. So this is a fairly common type of statement. It's something that you're probably used to. It shows up in everyday language, where you have one particular statement or truth or property or something that follows from another one. So you can make a statement of the form if P then Q, right? So you might be able to say something like, well, we might make a statement made like this. Here's an English language statement, something like, if it is cold, I will wear my jacket, right? Something like this. Well, okay, often we're kind of lazy in our English language, right? We sometimes skip the then. The then belongs right there. So there are two statements that are connected together here, right? It is cold, and the statement that I will wear my jacket, and there's the connection between the two. So now notice that there are certain things this says, and there are certain things that it doesn't say. So what this does say is that given the premise that the weather is cold, and I mean now this is still sort of an ambiguous statement, right? Because cold is subjective. You know, a Manitoban's definition of cold might be different from somebody from Vancouver, for example. But given this premise that the weather is cold, we are making the claim that given that the weather is cold, I'm going to put on my jacket because I want to be comfortable when I go outside. This says nothing about what would happen if it's not cold outside. It might be the case that even if it isn't cold, I'm still going to choose to wear my jacket. Maybe I know it's going to be cold later in the day. Maybe it's just a good-looking jacket and I want to wear it. Right? So it really only tells me what's going to happen in this case where the weather in fact is cold. And so the only way that you could disprove a statement like this would be if you happen to see me outside without a jacket on a cold day. And again, it's an English statement. There's a lot of subjectivity here, and this isn't something that you could really, establish as true. Mathematically, you're looking for statements where once you've made this assumption P, whatever P happens to be, P is usually called the hypothesis. Once you've made that hypothesis, you can proceed via some sort of logical argument to the conclusion that Q must also be true. So this is the idea with the conditional statement. So we'll see some of these sorts of statements as we move forward through the course. Another type of statement which is quite common is a so-called universal statement. So a universal statement is something that comes up when you're dealing with one or more variables, and you have often an identity or something like this where you want to make the claim that some particular result is going to hold for all possible values of those variables, right? So a universal statement isn't going to apply to an equation like 3x plus 2 equals 7, something like this, because there's one value of x where that statement happens to be true, and for every other value of x, it's in fact a false statement, right? So the truth of that statement depends on the value of x. There are other statements where there are variables involved, but nonetheless, as long as there's some agreement over what the sort of universe of objects you're working in is. So, for example, if I know that I'm discussing here only real numbers, and I make the statement that x plus y is equal to y plus x, that's something that we can all agree is true, right? And it doesn't matter which numbers I happen to put in there. We will all agree that yes, x plus y is equal to y plus x, and it's not going to be the case that, for x equals 2 and y equals 7, this happens to work out. But if I had chosen, x equals 5 and y was equal to negative 2 over 3, then suddenly it doesn't work anymore. When we say that it works for all values of x and y, we're saying that, this is universally true. It doesn't matter what you plug in, it's always going to work. And because you're trying to make these sorts of universal statements, things that are going to be true for all values of certain variables, and if you're dealing with variables, say like real numbers, where there are in fact an infinite number of possible values, well, then you can't just sit down and prove this by checking each possible value. You'd be at it for quite a long time. So if you wanted to, prove this, one thing that the important thing to note is that you cannot establish the truth of something like this with an example, right? You need to come up with some sort of general argument, and it's probably going to be some sort of general argument in terms of whatever variables you're working with. On the other hand, if I wanted to disprove a statement like this, I could disprove a statement if I can find one example where it works, right? Because I'm making the claim that this is something which always works. So if there's even one time where it doesn't work, then I know that this statement has to be false. So we can disprove by finding an example where the statement fails. And an example where it fails is usually referred to as a counterexample. And one of the ways that once you get into obviously more complicated things where the truth of a statement may not necessarily be clear, and there are results which have been outstanding for decades that remain unproven. There are other results where people have written down proofs, but the proofs are so long and so complicated that teams of mathematicians have been going through the details for years, and they're still not 100% sure whether or not the argument is airtight. But one of the ways that you can blow apart somebody's work, where somebody thinks they've proved a result and they've got something that they think is true. If you can come up with that one example that shows that their result doesn't work, then it doesn't matter what sort of arguments they propose in the other direction. As soon as you find that one example showing that their result is false, and there's nothing they can do about it. Okay. Another type of statement that you run into is an existential statement. So this is the claim that a particular object exists with a particular property, right? So I could make a statement like, let's say there exists some x such that 3x plus 2 is equal to 7, something like this, right? And even there, when you're making sort of an existential statement like this, you have to take some caution. I've got to tell you some sort of context here. What types of x are we talking about? What types of values are we considering for this variable? Are we considering integers? Because if my claim is that there exists an integer that satisfies this equation, then my claim is false. There are no integer solutions to this equation. If I'm claiming that there is, say, a real number solution or even a rational number solution, then my claim is true, right? Because this is true. And the way you show something like this is true is by giving an example that shows that it works. So the way you would prove a statement like this, and usually what you do is you do some rough work on the side, right? The way that you would kind of come up with this is, okay, you'd say, okay, over here on the side, you'd play around, you'd be like, okay, so 3x, I would subtract 2 from both sides is equal to 5, and then you'd say, okay, so x should be equal to 5 over 3. And so we'd say, yes, of course, the answer is x equals 5 over 3. But in fact, what you've done here is the logic is not quite right, because what you've done here is you've started out by assuming that there was a solution, and assuming that there is a solution, you can come to the conclusion that that solution has to be equal to 5 over 3. So I guess what you've established here is that if there is a solution, it's got to be 5 over 3. So I suppose you've shown that that solution has to be unique. But the way you kind of turn this around is the way you show that something exists is you show it to me. So you say, okay, well, here's something that works. So you say, all right, consider x equals 5 over 3. Well, then we have, so 3x plus 2 would be equal to 3 times 5 over 3 plus 2. So 3 times 5 over 3, that's just 5, equals 5 plus 2 equals 7, which is what it's supposed to do. So that's how I know that such a number exists. You probably do some sort of work to figure out, well, if it does exist, what does it have to be? And then you show that it works. Now this is kind of a nice proof because it's a so-called constructive proof. I actually explicitly tell you what the number has to be. There are other cases where using, say, bigger theorems. In calculus, there's some examples of this using things like the intermediate value theorem, where you can prove that something exists without ever being able to figure out what that something actually is. It's sort of a kind of a strange scenario, but it's something that can come up. Okay, so let's do a few examples showing how some of these results work. So here's an example using the notion of subset, which was introduced in some of the introductory notes. So here's the claim. So here's the claim. It's if A is a subset of B and B is a subset of C, then A is a subset of C. This is going to be the claim. So if one set sits inside of another set and that set sits inside of a third set, then the original set must sit inside that larger set that contains both the other two. Seems quite clear. And you might expect that a proof here is pretty straightforward, and it is. So the way that you would set out trying to prove something like this, where you have an if-then statement, well, remember that in an if-then statement, whenever the hypothesis is true, the conclusion must follow. So the way you prove this is you start out by assuming that the hypothesis is true and deducing that the conclusion has to follow. And so the proof would look something like this. We would say, all right, suppose X is, let's not do that, sorry, getting ahead of myself. Suppose A is a subset of B, and suppose that B is a subset of C, right? So in fact, we're assuming two different pieces here. There are two pieces to the hypothesis, that A is a subset of B, and also that B is a subset of C. We're assuming those to be true at the same time. Now, often what you do at this point is you pause and you ask yourself, okay, what am I trying to prove? So you might even write that out. You might say, we want to show that A is a subset of C. And then you translate this. You say, well, what does it mean to say that A is a subset of C? That means I need to show the following. I need to show that if X belongs to A, then X belongs to C. Notice we actually have conditional statements within conditional statements, right? This definition of subset is itself a conditional statement. So we'll pause and we'll think about this for a second. What is it we need to do here? So we've made a couple of assumptions. We've got two pieces of information here, and this means we're allowed to use these. We're allowed to make use of them. And now we've got something else we want to establish, which is that A is a subset of C. So how do we establish that? Well, we establish this by confirming that any time we start out with something that belongs to the set A, it must necessarily end up as an element of the set C. So what do? We suppose that X belongs to A. All right, and we need to chase this guy around. We chase this X around until we catch it over in the set C. All right, so what can we do here? Well, now we know that X belongs to A because we've made that assumption. And remember, we've also assumed that A is a subset of B. And remember, if we assume that A is a subset of B, what we're saying is that every element of A is also an element of B. And so that means we know that X has to be an element of B because everything in A has to also be in B. But now we can repeat ourselves. Since X is in B, we know that now. And we also made the assumption that B belongs to C. Well, if X is in B and if every element of B is also an element of C, then it must follow that X is an element of C, right? And then we say, oh, wait a second, that's exactly what we needed to show. We needed to show that if we choose any element in A, it has to end up as an element of C, and that's what we have. And so we can write ourselves a nice little conclusion. We can say, well, that means that A must be a subset of C. Okay. So there's a little example working with sets. We're going to finish up with a couple of examples involving complex numbers. So here's another example showing that complex multiplication is commutative. So what would be the theorem here? The theorem here is that for all complex numbers, so let's say Z and W in C, Z times W is equal to W times Z. Now, the tip-off that this is a universal statement is this for all, right? So for all means this is something that's going to apply to every possible complex number, not just to some complex numbers, but to all complex numbers. So how do we establish that something like this is true in general? Well, we need to come up with an argument that doesn't depend on the particular values of complex numbers that we're working with. So if I wrote down something like, Z is equal to 2 plus 3i, well then I've already lost the game because I've chosen particular values, and I would be making an argument that depends entirely on those values, and there would be no way to reuse that argument for other values. So the way to proceed is to use variables so that I don't actually have to tell you which complex numbers I'm working with. So what I do is I do something like this. I say, all right, here's a proof. We let Z equal to, let's say, A plus IB, and we let W equal U plus IV, where A, B, U, V are real numbers. But I don't tell you which real numbers, and because I'm not telling you which real numbers they are, I'm not telling you which complex numbers I'm dealing with. And so if I can show that it works here, regardless of what values are assigned to those variables, then I know that I've got something that works in general. And so what we do here is I'm trying to show that this quantity on the left is equal to this quantity on the right. And now, one thing, here's one warning. Don't start by writing down that equation. Don't start by writing down ZW equals WZ. There's this tendency to want to write down that equation and then try to simplify it and end up with something that you know is true and conclude that you've done your job. This is faulty logic. You're not allowed to start out by assuming the thing that you're trying to establish. We don't yet know that this is true. We need to come up with some argument that shows us that it's true. So usually the right way to proceed is to start with one side of the equation and try to work our way towards the other side. So let's say I start with the left-hand side. So Z times W is equal to A plus IB times U plus IV. And so I multiply things out here, and I go, okay, so that's A times U plus I times AV plus I times BU plus I squared times BV. And so let's kind of simplify this. This is going to be AU minus BV. Remember that I squared is equal to minus 1. And then I've got I times AV plus BU. And now what you might do at this point, right, we don't yet know that this is equal to WZ, but if you're, maybe you get to this point and you're stuck and you don't know how to proceed. And so here's again where you might kind of give yourself a little box over on the side, and you say, okay, where am I trying to get to? So I'm trying to get to WZ, which is U plus IV times A plus IB, and if I multiply that out, well, that gives me UA plus I times UB plus I times VA plus I squared times VB. And maybe you simplify that and then you compare it to what you have and you realize, well, the only difference between the two is the order in which I've written down my A's and my B's and my U's and my V's, and I'm allowed to switch that order because, A, B, U, V, these are all real numbers, and we know that the order of multiplication doesn't matter for real numbers. And so the next line would be to say, well, this is equal to U times A minus V times B plus I times VA plus ub, and maybe if you want to, you add a little explanation in here, you know, saying, well, the reason I can do this step is because I know that this is a property of the real numbers. And then you reverse your steps. So from here, you would reverse through, you know, what you did over here, and you'd say, okay, so that reverses out, and I know that this is going to come out to be u plus iv times a plus ib, and that in fact is equal to w times z, right? And the whole exercise, it probably feels almost trivial, right? Because you're thinking to yourself, well, of course, the order of multiplication doesn't matter. The order of multiplication never matters. Well, it hasn't mattered on things that you've considered up till now, but just wait. There are going to be times where the order of multiplication does matter, and so you do in fact have to be a little bit careful about some of these things, and you have to check them. And like I've mentioned, the proofs seem trivial because to some extent they are trivial. We're not going to give you incredibly challenging proofs in this course. We want to give you simple proofs so you can get the practice of writing these things down without really getting bogged down in the details, right? We don't want to really hit you with the details. We want you to learn the procedure, the kind of general procedures that can work once you move up into higher level courses. All right, so that's an example with a universal statement. Here's an example with an existence statement. So we can say the following. Now this is actually a combination of things. We could say the following. So if z is a complex number and z is not equal to 0, then there exists, right? So this phrase, there exists, that's your tip-off that it's an existential statement. There exists some complex number w such that z times w is equal to 1. So in other words, w plays the role here of 1 over z. Now, you'll notice that this is an existential statement, but it's an existential statement within a conditional statement. And in fact, I could have also written this in a way where it was actually a combination of a universal and an existential statement. I could have also taken this first line here, and I could have said something like this. I could have said, for all complex numbers z which are not equal to 0, there exists some w such that z times w is equal to 1. So there are a number of ways that you can phrase this. Often conditional statements are hiding these universal statements inside of them, and unless stated otherwise, assume that a statement is meant to be as general as possible. And so if you're trying to prove something, you don't want to try and plug in numbers. You want to try and do it in the greatest possible generality that you can manage. So how would you write a proof for something like this? So you would say, all right, well, we introduce our complex number. Z is equal to x plus iy, where x and y are... So it would be fine for one of them to be 0, they just can't both be 0. If both x and y were equal to 0, then z would be equal to 0. So we want z to be non-zero, so we make this requirement, right? So I've either, I've assumed the hypothesis if you go with the first version of the statement, or if you like this universal version, right? The only condition I've imposed on x and y is that they can't both be equal to 0. So I'm doing this as generally as possible. And again, we kind of know this setup. If you've gone through the procedure for division, we know how this works, right? We say, okay, I take my complex number z, and so I take x plus iy, well, 1 over it, right? So I want something that looks like 1 over x plus iy. And we do this trick, right, where you multiply by the conjugate. So we multiply by x minus iy. X minus iy, and we say, okay, so that's x minus iy, And as usual, the nice thing about multiplying by the conjugate is that you get x squared plus y squared on the bottom. And because x and y are not both 0, we know that that's going to be non-zero. And so we know that this sort of thing works out. But again, with the existential statement, what you want to do is you want to exhibit your numbers. You want to provide this w, and then you want to show that it works. And so then we consider w. So we're going to let w equal x over x squared plus y squared plus I times minus y over x squared plus y squared. And now we just have to show that this works. So we say, okay, well then z times w would be equal to x plus iy times x over x squared plus y squared minus iy over x squared plus y squared. And you multiply everything out. I'm short on space, so I'm going to leave some of the algebra to you guys, but you can check that if you multiply it out, the first term you're going to get x squared over x squared plus y squared. The imaginary terms are going to cancel out, right? I'm going to get when I do this guy, I'm going to get minus ixy, and then when I do this guy, I get plus ixy. Those terms cancel out, and then I get minus I squared y squared over x squared plus y squared. But as usual, I squared is equal to minus 1, so this minus I squared becomes a plus sign. And then I've got x squared plus y squared over x squared plus y squared, so that works out to give me 1 as needed. And so that way I've demonstrated that for any non-zero complex number, I can find another one so that when I multiply them together, I get 1. I guess the one thing I didn't make explicit here, and maybe again because of space, is the fact that, well, the reason that this number w is defined is that x and y are not both 0, and therefore x squared plus y squared is non-zero, and that means it makes sense to divide by x squared plus y squared. Okay. I'm going to leave you with one more. I'm going to give you a property of the complex conjugate, and I'm going to maybe get you started, but I'm going to leave you to finish the proof. So here would be one of the theorems you might try to prove. This is going to be a universal statement. For any complex numbers, z and w, the complex conjugate of z plus w is equal to the complex conjugate of z plus the complex conjugate of w. Now the proof is in the textbook, so you can look it up there, but give it a try yourself first. The way you would try to prove something like this, the proof you would write down, you would start with something like, you would say, okay, you want this again, you see the for any, so you know it's universal, and so you want to give a general proof, and so you would say something like, all right, let z equal to x plus I y, and let w equal to u plus I v be any two complex numbers. So you start with something like that, and then you choose one of the two sides of the equation to start with. Let's say you start with the left-hand side, and you're going to have to, work things out. So you replace, so we said z is x plus iy, so we put x plus iy in there. We said w was u plus iv, so we put u plus iv in there, and we take the complex conjugate of that. And there's going to be a few more steps. You've got to fill in the algebra. Now, the way this is written, this is telling you to do the addition first and then take the complex conjugate. And what you're trying to show is that that's the same thing as if you first do the complex conjugates and then do the additions to end up with z bar plus w bar. So there's a couple steps of algebra in between there that I'm going to leave for you to fill in. And that's it for this video.